Hello. In this video, we're going to introduce a power generation plan. So we're going to see each of the components separately and then put them together. Let's start with our first component, which is going to be our pump or a compressor. So this component, to operate, we need to offer work. So I have here the arrow WP for pump, okay? And what it does is it takes fluid at low pressure and it increases its pressure and enthalpy here. So on the TS diagram, the compressor takes our fluid from point 1 to point 2. Okay, so that's the ideal compressor without any generation of entropy. Obviously, there are irreversibilities. So if this red line represents our constant pressure lines, our isobaric lines, our true process is not perpendicular on the TS diagram, but instead it deviates a little bit to the right. We can always create entropy, but we can never destroy entropy. So we'll call this point 2S and this point 2. Now, based on this graph, we can introduce the isotropic efficiency of the compressor. So this is going to be N P equals H2S minus H1 over H2 minus H1. The work that we need to offer to the compressor per mass flow rate, so W dot P over M dot equals H2 minus H1. Now, in the case where we have a reversible process, only then we can assume that this work over M dot equals the specific volume times the change in pressure. Or graphically, on the PV diagram, we start from point 1 going to point 2. The work will be this area, only in the reversible case. Now let's move to our second important component, which is going to be the expander or turbine. The expander or turbine works the opposite way than the compressor. So we give fluid to our expander at point 1 of high pressure and enthalpy, and we get the fluid at point 2 with lower pressure and enthalpy, but in the process we got a lot of work out. And we do all this cycle to generate this work and generate electricity. on the TS diagram, the process is kind of opposite of that of the compressor. So we're going to start from a high pressure, P1, and ideally move isentropically, so vertically down to pressure P2, to point 2. But this is not very likely. We usually have irreversibilities, in which case we'll deviate from point 2s, and we're going to move sideways to point 2, generating some entropy in the process. Exactly as we did with the pump, we define the turbine isentropic efficiency, Nt, as H1 minus H2 divided by H1 minus H2s. And the rate of work production at the turbine divided by the mass flow rate equals H2 minus H1. The next important component is the boiler. You may hear it as a heater or a combustion chamber. What this does is it takes our fluid at location 1, and under constant pressure, this is a safe assumption to make that the pressure remains constant, we exit at position 2 at higher temperature and thus entropy. So on the TS diagram, we're moving on an isobaric line from point 1 of low temperature to point 2 of high temperature. Exactly in the opposite way, our condenser works, in which we feed our fluid of high temperature 1, and we get our fluid at low temperature 2, again moving on the same pressure line. So on the TS diagram, we start from high temperature to low temperature 2. So now, with the 4 simple components we learned, the compressor, the boiler, the expander, and the condenser, we can put together our first simple power generation plant. So we'll get fluid in the compressor at position 1. Okay. The compressor will compress the fluid and exit at 2. So we said this process happens ideally isentropic. So we'll go from point 1 to point 2. Then we'll feed this fluid in the combustion chamber, where under constant pressure we're going to increase the temperature. So we leave at point 3. At point 3, we'll take our fluid and feed it to the expander, which again theoretically isentropically will reduce its temperature, and exit at point 4. And from point 4, we'll take our liquid, feed it in the condenser, and the condenser will reduce the temperature again at constant pressure and complete the cycle at point 1. So these are most simple cycle. We can find the efficiency, the overall thermal efficiency of the plant as N equals, on the top will be what is useful for us, which is the total work. So the total work is the work of the turbine minus the work of the pump. Okay. Turbine minus work of pump. This is the useful, and the cost is the heat we pay in the combustion chamber, Q dot. We can substitute all this with the enthalpies we found there. So we'll get H4 minus H3 for the turbine, minus H2 minus H1 for the compressor, divided by H3 minus H2 for the boiler. Obviously, if we take reversibilities into account and we change the compression process from 1 to S to 1 2, and the expansion process from 3 4S to 3 4, then this efficiency will change. Okay. In the next episode, we're going to watch two more components of power plants, the heat exchangers or preheater and throttling devices, and we're going to talk about more complicated cycles. Thank you.